Okay, so today's lecture is on more and more advanced GANs, right? So we remember from last time that GANs came on the scene originally in kind of the range. Last time we were talking about kind of between 2014 and 2016, right? The Goodfellow paper, followed by a couple other papers like the Wasserstein GAN. That was like the starting point, right? And then after that, there were dozens and dozens of developments in GANs, right? So this is kind of like followed by kind of an explosion of interest, which continues to this day, but certainly kind of between like 2016 and 2020, say, there were just dozens of GAN papers and GAN innovations. Because remember that really the only thing that characterizes a GAN is, the generator block and the discriminator block, right? If you have those two things, then you have a GAN, right? So there are lots and lots of ways to think about what the architecture of the generator might be, how the discriminator might work, all sorts of ways to think about how that might go together. And so what I want to talk about today are just a few of the key high point innovations in the GAN world. We're going to talk about some more on Monday also. And of course, there are more details in the book, and there are more details in the original papers. And so let me just flip to the browser real quick. You can see that I've linked to all of the papers I'm talking about today in the reading section, and then also some useful links over here. So, and I believe that Foster chapter 10 is the chapter that covers some of these advanced GANs, but not everything that I'm talking about today is in that chapter. Okay, so let's talk about some of the high points, right? So one of the first ones was called ProGAN, and this kind of came out of NVIDIA in 2017, right? And so one thing that you noticed from the VAEs, for example, and from the very first GANs is that the image size that you could generate was pretty small, right? And so the first thing that people wanted to do was scale it up to be like high quality, like 1024 by 1024 images, okay? But it wasn't really possible to directly apply the GAN methodology to these huge images like right from the beginning, like to generate a 1024 dimensional image directly wasn't so easy at the time, right? So instead, the key innovation of ProGAN was to basically progressively train the GAN. So the pro stands for progressive, from low resolution to high resolution. For example, the output of the ProGAN might be a 1024 by 1024 image. And so the kind of fundamental idea was, you start with a very, very low resolution GAN, right? I have a latent vector. And remember that this is, kind of like the key thing of the generative model, right, is that we generate a new image by choosing this random vector or random image. And so in this case, for example, we might use a 512 by 1 noise vector, like a Gaussian noise vector. That's kind of what we've been doing so far, right? We put that into our generator, and the first generator we makes a very low-res image, like a 4x4 RGB image. And then we put a 4x4 image into our first discriminator, and what comes out is a score in the range 0 to 1, okay? And so we can train both this generator and the discriminator on our original training set. Even if our training set originally was high resolution, we could just downsample everything to 4x4 and then train this very initial generator and discriminator, right? And so obviously, this is not going to be that exciting, right? Because 4x4 images are not that great. But maybe we'll learn something about the very, very low resolution arrangement of pixels. Like you can imagine that if you really squinted your eyes and looked at a super blurry version of the image, you'd still learn something about like what pixels are kind of like foreground, what pixels are kind of like background, right? So we start with this low-res 4x4 thing, and then we kind of upsample the images and we move on to an 8x8 scheme, right? So the next stage is then we kind of upsample everything to an 8x8 version, right? So the idea is that we have our same latent, the same 512 by 1 dimensional vector, we have the 4x4 generator that we learned before. And then what we could do is we could upsample that image, which produces an 8x8 image. And also, I could kind of take the generator and I could pass it through a new generator that I now train, right, an 8x8 generator. And then what I kind of do is I combine these two things, right? I say, okay, I'm going to weight this top branch by 1 minus alpha and this bottom branch by alpha. What comes out then is an 8x8 RGB image. So initially, alpha is small, right? So, initially, alpha is small. And then that alpha eventually goes to 1, right? So the idea is that I don't want to throw away what I learned at the 4x4 version. I start with that, and then as I learn more and more about the 8x8 world, I slowly turn the slider from my 4x4 branch to the full 8x8 branch, right? So in the beginning, I'm mostly on the 4x4 side, and then I start to move the slider all the way to the 8x8 side. So by the time I train this 8x8 generator, now I've got a machine that can generate 8x8 images, right? And at the end, I basically just throw that top branch away, and now I've got an 8x8 generator, right? And in the same way, the discriminator kind of works in a similar way. It's kind of like saying I have an 8x8 image. I could downsample that image to get a 4x4 image, and I could put that through my 4x4 discriminator that I already learned, which can make a decision. Or I could put this process through like an 8x8 discriminator. And again, I kind of simultaneously am training these things. Where again, initially I put all my weight on the 4x4 branch because I know the 4x4 branch knows what it's doing. And eventually, as I train this stuff together, I move my slider over so that now I've got a discriminator that only works on 8x8 images, right? And I just keep on doing this until I get up to the 1024 by 1024 scale, okay? And so basically the idea is that I kind of like at every next higher up resolution, I kind of wait until things stabilize at that next resolution, and then I move on by adding another branch at the next higher resolution until I get all the way up to where I want to be. And so that's kind of the basic idea, is this, instead of making a 1024 by 1024 image in one shot, I do it in a series of resolutions, right? So at the end, the whole hierarchy, if I look at the original paper, which is over here, so opening, arguably I should have downloaded this before we came. It's getting there. Sorry. So go back to this while we're looking at something while I'm waiting for this paper to download. And so there were other innovations besides the hierarchical, setup. That was the main one. But there were also a few extra contributions that related to how you should tune your learning rates, what normalization you should use, how you should do batching. A lot of that kind of like under the hood stuff that is, boring but important, right? And I'm not going to really talk about those innovations here. I'm just going to talk about the paper itself, right? So if I look at the paper, eventually what you kind of see is this kind of picture, right? Where initially I have, let me make this a little bit bigger. Initially I have my 4x4 model, then I learn my 8x8 model, and eventually the latent kind of bubbles all the way up to a 1024 by 1024 model, and then the discriminator kind of has the same kind of structure. So I've got this kind of funneling structure that goes from low res to high res. And there's lots of details about exactly how this process works. And here you can kind of see like what these 1 minus alpha and alpha branches are doing. So again, for more details, take a look at the actual paper. This is a very hand-wavy version of how it works. Now, let me just say that this paper at the time, which was, 2017, took 4 days to train on a single powerful GPU, right? So already, that's the kind of thing still you could do in a well-equipped computer lab, right? But one of the things we're going to see, and this is certainly true as we go to the age of diffusion, is that to get this great performance requires more and more beefy machines and more time, right? To the point that now, to be able to train DALL-E 2 and the DALL-E 3 that just came out, I'm sure requires days and days of some crazy, Terra processor array kind of thing, right? So this is the kind of thing that you could train on your own, but probably, you may not want to, right? And then with GitHub and repos and so on, now you can do things where you can download the weights of these things and start to play with them, right? So the next big innovation was StyleGAN, right? And so some of you may have already heard about StyleGAN. So StyleGAN, again, was an NVIDIA innovation, pretty much, in 2018. This was a big step forward, okay? And so one of the things that people want to do with GANs, right, is to not just sample from the latent space, but also to kind of create images that are more like what the user wants, right? So if you just sample a Z value, you don't know what you're going to get, right? You kind of want to start to learn how to push the GAN around to make images that are of the kinds of things that you want, right? So the key idea was, key issue that this addressed was called entanglement, which you'll see in GAN papers. So part of the idea is that we want to investigate kind of high-level attributes in the image space, right? So for example, I want to have a knob that, when I turn this knob, it turns the person's head left and right. And I have this other knob that changes them, from blonde to dark hair, right? But the problem is that there's nothing innately in the GAN control that forces those attributes to decouple, right? So in some sense, I might end up with a knob that says, okay, well, if I turn this knob, it will rotate the person's head, but it will also change the background color of the image, right? So the idea behind StyleGAN was to say, okay, we want to try to push attributes apart in the latent space, okay? So the idea is to try to decouple image attributes for kind of more, I guess I would say, direct control. And so kind of what you want to do is you want to disentangle the latent space, okay? And so StyleGAN did this by introducing kind of like a second level latent space, right? So StyleGAN introduced what are called style vectors. And again, personally, I find the phrase style vector to be a little bit certainly ambiguous, and I find it confusing, right? So for example, when I think about style, I'm still stuck in the mental image of the stuff we talked about in lecture 2 about okay, I want to make a Van Gogh looking image, right? And Van Gogh is a style. That's not really what they mean here for style. It's kind of more like, well, when I show you some pictures, it'll become a little more clear what they mean by style, but it's a little bit confusing just in general, right? Basically, the idea is that these style vectors affect kind of apparent image features at different scales that we can kind of put labels on in terms of words, right? So high-level stuff like head orientation and low-level stuff like wispy hair and stuff like that, okay? So the key, I'd say introduce style vectors into the generator. Basically, the discriminator was basically the same as the program discriminator. So again, this builds on top of this idea of being able to generate very large images, right? But the key thing was, what does this style vector mean? So how does this new generator work? So the generator introduces this concept where I have my latent space Z. And again, this is where I generate my Gaussian random vector, right? So this is totally just like noise, okay? Then I have another network that I learn. This is basically what we call a mapping network. And that mapping network produces another vector W, right? So here, in the original StyleGAN conception, this is basically like a fully connected deep neural network, right? And this is trainable. So what I do is I try to learn a network that transforms the latent vector into some other vector. And this is like a intermediate latent space. And the hope is that if my mapping network did a good job, that navigating in W is less entangled than navigating in Z, right? Makes the features more separable when I turn the knobs, okay? So part of StyleGAN was training this new middle network, this mapping network, and then I take the W that comes out, and then I feed that into the network at different resolutions, okay? So this is kind of like one key idea. The other key idea is that I take this W, and then, again, since this is a progressive generator, this basically is going to go and leave some space on your paper if you're taking notes, right? So this goes through a block called A. This A is just basically like an affine transform. So it's kind of like a scale and a translation of the vector that I put in, affine transform. So it goes through this affine transform. What comes out is what's called a style vector. And this goes into a 4x4 block that generates a 4x4 image. And also, there's some noise that comes into this generator, right? So this is kind of like one low-level thing. And then I do the same thing. I have another affine transform that goes into an 8x8 block. And also, this 4x4 thing kind of gets upsampled here. And I add more noise here. So I'm just trying to sketch, like, how do I transform this program kind of structure into something that eventually is creating a 1024 by 1024 image, right? So I keep on basically upsampling what I get until I come out of here, right? And so the idea is that the W is playing the role of the latent, right? It's controlling what is happening in each of these resolutions. And then there's some noise here that makes it so that the generation is not entirely deterministic, right? So for example, one of the things that you know if you've ever used like DALL-E or Midjourney or something like that is that if you put in a prompt and you ask for something, you basically get a bunch of variations on the theme, right? So you can think about the same kind of thing happening here is that, if I'm up here at, kind of mid-resolution, say like 512 by 512, I can think about the noise vector as going to introduce things that are varying at a fine detail. So say I'm generating faces, different noise vectors may generate like different patterns of freckles on somebody's face, right? So the big structure of the face is the same, but changing that noise vector produces like kind of slightly different arrangements of fine level details, right? So it gives me a little bit of variability, okay? And so the result was something like this. Let me look at my PowerPoint here. So these were the kinds of images that StyleGAN could create. Now still, you were in the world of training a StyleGAN for specific classes, right? Just like what you did on the homework, right? So there would be like a car StyleGAN and a bedroom StyleGAN and a cat and a dog StyleGAN, right? And these are all StyleGAN samples that were drawn from these classes, and they look pretty good, right? Some of them look a little bit weird, like this cat here is probably a little bit like deformed, but in general, this was a big step forward, right? I guess these are all cats, there are no dogs here, right? And so the cool innovation of StyleGAN was this idea that, just like we talked about, one of the cool things that you can do in latent space is interpolate between two faces or two cats or whatever like that by kind of like traveling along a vector that goes from Z1 to Z2, right? You do the same thing with StyleGAN, except the clever idea was that you could basically decide how to, kind of at what level to do the mixing, right? So you can kind of morph between two faces or two objects at different kind of layers, right? So let me kind of be a little more explicit about that. So kind of the idea would be that, I have my network. The old version of this network would be to say, okay, I put the same W into all of the branches at all the resolutions, right? What I could do instead is that I could say I'm going to draw a line here, and above the line, I'm going to put in, the vector W1 that comes from person or object number 1, and below the line, I'm going to put in the W that comes from some other person, right? So it's kind of like saying I'm going to use the lower level attributes from W1 and the higher level attributes from W2, right? So instead of like averaging two faces together, I can kind of say, well, what is the combination at different scales, right? So the idea would be that this is kind of what they call the crossover point. And the observation was that basically the G network uses the latent W1 before the crossover point, and the latent W2 after the crossover point. And so, it's easier to show with a picture than with words, of course. So here's kind of an idea, right? So here, this is like saying, if I draw the line fairly low, right? So if I draw the line for low resolutions, kind of what ends up happening is that I have, taking the low-level stuff from source B and the rest of it from source A. So it's like, if we look at one of these rows, it's like saying, I'm kind of taking the, the hair color and the background color and the, kind of like skin color of source A, and then I'm applying it to, these kinds of people in source B, where here I'm keeping basically whether they have glasses or not, whether they're a baby or not, what gender they are, right? And so here, this is kind of like saying, take this coarse stuff and apply it to these kinds of things. And if I instead do that at the higher level, right? So if I instead choose something that's a little bit further down the pole, then it's like I'm more or less taking, everything from here and only changing very coarse stuff from here, right? So for example, here, if I look at the very lowest column, this is like saying this woman's face is not really changing, but what I'm doing is I'm inheriting basically the coarsest stuff I can from this source, right? So I'm not changing that she doesn't become a baby or anything, but she gets blonde hair and the background turns kind of blue to correspond to the fact that that's the coarsest stuff that's going on in source B, right? And then in the middle, you kind of get these kind of like, intermediate morphs, right? Where, it's kind of hard to exactly say what's happening, in this row or this row. Pieces are getting taken from both sides, right? And so I think that the easiest thing to look at is, if you take the finest level, you're basically changing the, the background color, but the head pose and the expression isn't changing. If I go back to this picture, the original picture, I'm taking the head pose and the expression and everything from the top row, and I'm only inheriting the kind of facial coloring and the hair color and the background from this row, right? And so, this became kind of cool where it's like, okay, I can kind of decide not only if I want to morph between two things, but where I want to draw the line. And it's certainly not just a like cross-dissolve kind of morph. I'm also doing things like, expression changing and rotation and so on. So you could kind of say, okay, I like this picture I generated with this GAN. Now I just want to rotate their head a little bit to the right, right? And I could just do that by taking a picture of someone whose head was turned to the right and just taking that kind of head pose off of that and transferring it onto the thing that I had, right? So it suddenly became a very cool, way to screw around with editing, right? Okay, so that was definitely a big innovation, was StyleGAN. When that came on the scene, people really started to take notice. And also, the images are looking more and more realistic, right? So again, we're using the power of progressive, growing. So these are like 1024 by 24 images, and they look pretty good. We're starting to get to the point where you might not think that these were computer-generated images, right? There were still some errors, though, that if you kind of look closely at some of the things that StyleGAN produced, and this is like really subtle stuff, but like, this was like a little bit of a blotch, right? And apparently StyleGAN would occasionally throw off these characteristic little blops, right? And so the very next year was StyleGAN 2, right? So that was the next innovation by many of the same authors at NVIDIA. So StyleGAN 2 in 2019, they basically updated both the generator and the discriminator to improve the overall look of the images that were produced, right? So, updated both G and D to address, image artifacts from the original StyleGAN. So those little blops and bubbles that you sometimes would see in StyleGAN1 output were no longer there, right? Also, there were some, kind of differences, like, they, at this point, were able to do it without progressive training. So the kind of program architecture kind of went away. And instead, they used residual and skip connections to achieve high resolution output. And then the advantage of that was that that took away one big kind of tunable thing about program, which was having to decide how do you move that alpha slider over time to transition from one resolution to the next. Now they didn't have to worry about that at all, right? Even though it wasn't progressively trained, they still were able to preserve the kind of desired behavior where first the GAN is learning the low resolution layers or the low resolution stuff, and then later on it learns high resolution stuff. And kind of the idea is that, at first the generator, first the generator can first the discriminator can make choices based on low resolution problems, right? And eventually, as you keep on training, the discriminator will naturally move forward to picking on really fine details. So in that way, implicitly, the low resolution stuff kind of gets ironed out first before the high resolution stuff is trained. At least that's my understanding of it. Question?
Yeah, as these GANs were getting more sophisticated, was the data used to train them getting more sophisticated or bigger?
That's a good question. So was the data changing? And actually, that's a good question. And let's just take a look. I'm not 100% sure what the difference in training data was between, for example, StyleGAN and StyleGAN2. So let's just take a look for a second. So this is StyleGAN2. And here are the blips and blops. So I'm curious to see where the training data part is. Oh, I missed the part about training. Well, actually, I take it back. Maybe the training is somewhere in the, actually, while we're talking about training, here you can see that this StyleGAN2 used about 51 single GPU years of computation, which turned out to be kind of things like 9 days or 13 days, right? So definitely, this is not the kind of thing that anyone could really train feasibly on their own, because this is some sort of like, crazy system, 8 Tesla V100 GPUs working for days at a time, right? That's not the kind of thing that we could probably do here at RPI. The question is, what is the training data, though? And I'm wondering where that's talked about in the paper. It wouldn't be surprising to me if the training data was also bumped up as we went on in time. I don't think that they used just the very same training data. But looking at this, I don't actually see on a quick browse where the training data is mentioned. Actually, I don't think that this paper that I cited includes the appendix, which has all of the details on it. So I would say put a pin on that, because I'm not exactly sure what the difference was. I mean, it was only a year later, so I don't think the training data could have been that much different. But I'm not sure. Yeah.
So Professor, for the StyleGAN paper, the structure,
Mm-hmm.
You mentioned that they were using like a Polytechnic layer to project the original noise into like a latent space,
Mm-hmm.
and then they use the same latent code to different levels of the upsampling generation blocks, right?
Right.
With different affine transformation. So I'm wondering, because different level will definitely control different attributes, such as like the apples or like more detailed like freckles or something. But they are kind of use the same dimensionality and then apply nothing but like a affine transform. So the dimension is still the same. And how they can so I feel like the feature is not like really disentangled, or like maybe like certain dimension control like a set of different attributes at different levels.
Right. So kind of to try to kind of encapsulate this question. So the same W is kind of coming into the network at different levels, right? And what's changing at different levels is this affine transformation. So the A part is changing per layer. So you really are changing the latent that goes into every one of the blocks, right?
Dimension doesn't change.
No, the dimension doesn't change.
Yeah.
The W is always the same dimension,
Yeah,
right?
So for example,
Oh, I kind of see what you're saying. So you're saying that, the whole point of the Z to W network is to disentangle, right? And then the question is, okay, so if I have like the first element of W that's already kind of theoretically disentangled, then what's happening at these different layers? Well, one thing I guess you could think about is that the affine transformation could like zero out different elements of W at different levels, right? Like the trainable A could do that if you wanted to, right?
And then at each layer, after a fine transformation, it would be kind of sparse. Is that what you're saying?
Oh, well, I guess, well, since it's trainable, I guess you're not really putting any sort of like sparsity like prior on making sure that like only certain elements of W are selected. I don't think it actually works like that, right? I mean, in theory, what you could do, and I think I'm going to talk about this in other things, is that in theory, you could just put in different W's to different layers of the style network, right? And I think ultimately, that's a different way of looking at it, right? So there's no reason why you have to take the same W and push it through these affine things to change it for each layer. Instead, you could just use entirely different, like W1, W2, W3 for different levels, and that would be more explicit decoupling, maybe, right? Of course, you still have to get from the original Z to each of these W's, right? I'm not exactly sure how that would work, but yes, you don't necessarily have to apply the same W at every level. But as for how exactly the W decouples at each of the resolutions, that I'm not totally sure about. Like if you were to analyze what parts of W were being used at every level, you'd have to drill down and actually look at that, right? I don't want to raise the specter of like attention, right? You can imagine that every level is kind of like paying attention to different, parts of W via this affine transformation, right? That's by speculation at least, right? So yes, I'd have to read more though to totally understand the answer to that question though. Hopefully that makes sense. Other questions or comments? So there's obviously a lot of architectural stuff that I'm glossing over because clearly the pictures I'm drawing on my piece of paper don't look like as detailed as this, right? So I'm trying to give you the high level, like what is new and interesting about each of these GANs. The last thing I want to say about StyleGAN 2's innovation is that, there was also there were some changes to how the network was normalized. And so, for example, one of the things that you can see in this paper was this block called ADA-IN, which stands for Adaptive Instance Normalization. This is a particular way of taking the outputs of one layer and normalizing them in preparation to be input into the next layer, right? And there's a specific way they did that that turned out to have impact on the visual quality of the StyleGAN 2 outputs. But then, a couple of years later, I think that it was observed that actually you don't need this thing. So it's one of these things where people are constantly just like tweaking different aspects and saying, okay, what do we need, what do we not need, right? So I don't want to dwell on any particular thing because maybe that thing will not be that important in 2 years from now, right? But I think the big picture is what I'm trying to get across. One other thing I want to say about the big picture here that I thought was worthwhile is that there's also a loss function modification that includes basically a term, something like this. It's like saying I have the expected value of, let me write this down first and then I'll interpret what this means. So kind of like this is saying is that this here is the Jacobian of G, the generator, with respect to W. And this Y here is just some noise image. And the reason for this term is basically saying that, I don't want a small change in W, or I don't want a small change in the image to produce a large change. I don't want a small change in the latent space to produce a large change in the image, right? So I basically want to be able to walk around the latent space and say, okay, if I move 0.2 that way, it's not going to generate some crazy change in the image versus moving 0.2 in the other direction, right? So it kind of makes exploring the latent space more consistent, more predictable, right? And so this is just kind of like a boundary on how much things can change as I move around the latent space. So when StyleGAN 2 came out, suddenly, you couldn't train it yourself, obviously, but you could use it, right? And so suddenly people started to use it for all sorts of crazy stuff. And so, one of the things that you may have seen is, I think I mentioned this last time, this famous, this person does not exist website is based on, I believe, StyleGAN2, right? So like as I generate these pictures, and they're being generated on the fly on some computer somewhere, these are all just like totally synthetic people that came from the StyleGAN2 network, right? And for the most part, they look pretty convincing. The backgrounds may look a little bit weird. Like here's one where this is a little bit some sort of crazy thing. Let's move off of this, right? But for the most part, they look pretty good. And then I found this video of interpolating the StyleGAN. This is basically just moving through StyleGAN2 latent space, just like generating morphs between all sorts of random people. Every single frame of this looks like a pretty credible person, and it's mesmerizing to just watch like the noses moving back and forth and glasses coming in and out and ages changing and races changing. It's pretty crazy, right? And so, of course, this definitely makes you think about trustability of images, right? Like I think that people make like faked LinkedIn profiles and fake profile. I mean, this is like if you wanted to grab a face, you could just make one, right? And again, now we're getting to the point where you could actually specify the kind of face that you want to make. And so you just sit there and watch this for hours, right? It's just like mesmerizing. And of course, some of the background stuff has some glitches, but generally it looks pretty good. And of course, before I move off of my webpage, let me also say that there used to be a website called Awesome Computer Vision, and here's a specific website called Awesome Pre-trained StyleGAN2, right? So you can go to this website and basically, if you want models for, all sorts of faces, cats, cakes, grumpy cat, Obama, and so on, right? Like you can just grab a pre-trained StyleGAN2 model that does that, right? Because a lot of these, classes came from computer vision data sets that had been created, before, and so some of these are specific to like this FFHQ is a famous facial image data set with different configurations, and so some of these are better than others. These are like messed up cars, right? So if you're interested in using StyleGAN2, you can just kind of like find the model that you want and download it, right? And one thing I'm recommending on the homework for using your own GAN is I believe that if you use the Runway ML, train my class, thing, I think it's basically training on top of the StyleGAN2 generator somehow. I'm not sure what class it's using for StyleGAN2, but I believe it's built on top of StyleGAN2. So again, it's totally infeasible to do on your own, but you can pretty easily download the weights that are out there. Okay, and so I think that it's probably fair to say that StyleGAN2 is still what I think a lot of people are going to think of as the state of the art in GANs, even though there was other stuff afterwards, right? So just to give credit where it's due, there were a bunch of other key GANs that you may have heard of. So there was one called SAGAN, which stands for Self-Attention GAN, and Big GAN was another one that came out of DeepMind. So each of these kind of introduced some structural innovations to the architecture. And these in particular kind of use an idea called attention, which I'm sure that maybe you've heard of if you've done any reading about like how GPT works. We're going to talk about attention for sure when I talk about natural language processing, right? So I'm kind of holding the concept of attention until we get to language, where I think it makes more sense, but then it can be used in vision also. There's also something called VQ GAN, right? So this VQ stands for vector quantization. We talked about VQ VAE. You can kind of do the same thing with GANs, right? So you kind of are replacing the GAN discriminator with a vector quantized thing. And then there's also something called VIT VQ GAN, where VIT means visual transformer. So if any of you have done any sort of computer vision, you may know that visual transformers are a big thing. We're also going to talk about transformers in the kind of language section of the class. So we'll talk about attention and transformers together. And so there were lots of innovations along these lines. I mean, I think that there's probably some library of like some kind of encyclopedia of GANs that you can find like all sorts of things, right? In particular, Big GAN I think is one that you'll definitely see when you come across. All right, so then this was kind of like one area of interest was just kind of like better and more authentic generation, right? That was kind of like what GANs were focusing on kind of in the couple years after they were proposed. Then we start to get into some stuff where we want to have better control over the GAN, right? So it's fun to move around through latent space, but how can we move in directions that we care about, right? And so one paper that I like a lot that came out of this is called GAN space. So GAN space was in 2020. And again, this was Alto University and people from Adobe. And so GAN space let you suddenly explore what certain movements in the latent space did and attach kind of semantic meaning to what you were doing in the latent space, right? So kind of the idea was, let's refresh, and it's built on top of StyleGAN 2. And I think they also had a version that built on top of Big GAN, right? So let's look at the StyleGAN 2 version. So remember StyleGAN 2, I take my latent space, now I create this kind of like intermediate latent space, and I can think of a network, like a generator network, as producing at layer I take what came out of the previous layer, and I take the input vector, right? So it's kind of like, layer I. This is the output of layer I minus 1. And then this is the style vector. And so the final Y, after I go through all the layers, is the final image. Okay. And so that's kind of the setup. The key kind of engine of GAN space was what's called PCA, Principal Component Analysis, right? So if you ever took a machine learning course, I hope that you heard the word PCA, right? Which is like one of the most fundamental things for machine learning. Let me just kind of like refresh with a picture. So this uses, PCA, stands for Principal Component Analysis. So the idea behind PCA for just like general machine learning is, suppose that I've got XY data, and it's just like a scatter plot on a page, right? So the goal of PCA is to say, what are the directions of dominant change in this data, right? I should be able to say, oh, this direction, V1, is the direction in which the data is changing the most. And this direction, V2, is the direction in which the data is changing the second most. In this case, it's early dimensions, but you can imagine doing this in high dimensions, right? So if I only had one number to describe a given data point, what I should use is the distance I've traveled along V1, right? That's the closest I can get. If I only give you one knob to tell me what data point I'm at, I shouldn't use the x value or the y value. I should use the motion along the V1 vector, right? Now, I can imagine doing this on the latent space of a GAN, right? But it doesn't make that much sense to do on the Z space, because the Z space is already, by its definition, a Gaussian random variable, right? So I mean, a Gaussian random variable is just a point cloud that's uniform in all directions, right? So I'm not going to learn anything by doing PCA on Z, but I could learn something by doing PCA on W, right? So I've learned W to be a better representation of what I should, of the disentangled latent factors, right? So the key idea of GAN space was to do PCA on W space after I've gone through this fully connected network. And then what I could do is I could move along these vectors in W space that I learned from PCA and see what happens, okay? And so what does happen? So let's go back to this picture here. So this is StyleGAN 2. So this is an example of just taking the first principal component that came out of StyleGAN 2 and just kind of like moving along left to right, I'm increasing the weight on that principal component vector. You can see that I start with a boy and I turn into a girl, right? So that one knob is basically changing the gender of the person, right? We didn't actually, specify that. That fell out of what was learned by the GAN, right? If I turn the second knob, the second principal component, and I turn that knob, I'm kind of simultaneously changing the gender. Now it's kind of going from girl to boy, but I'm also changing the head rotation, right? So I haven't kind of decoupled these two things that well. If I take the third principal component, Then as I change it, I'm changing the age of the person, the apparent age. The background is changing also. And also there's some subtle head rotation, right? So the kind of observation was that clearly moving in the principal components is changing the image in some sort of a explainable way, but it would be better if I could find directions that didn't have these kinds of like gender and rotation tangled up, right? So the observation was, kind of coming back to your question of like, do I have to apply the same thing at every level of the network? Instead, what I could do is I could say, okay, I'm only going to apply a principal component at a given level of the of the network. This is kind of like, before I go on, this is kind of like saying, here you can see that the top PCA components are clearly encoding all together, the shape of the cat, the head pose, kind of the rough background of wall, cushion, whatever. But then all the other PCA components are controlling the way the cat actually looks. And conversely, if I fix the first 8 components, or if I fix the last components, I'm kind of fixing the appearance of the cat. But then if I change the first ones, I'm going to change the way that cat looks, right? So it's kind of interesting to see how the components together are working. This was the kind of the key observation, though, right? Is that try to just apply the principal component at certain layers of the style GAN network. Then you can effectively just do one thing, right? So here in the first row, what I'm doing is just by applying the first principal component at the first 3 layers, I'm actually just kind of changing the rotation of the person without doing anything else. If I take the 10th principal component and apply it at the 7th and 8th layer, what I'm doing is I'm just changing the hair color of the person, right? So the idea would be that the user could kind of poke into the style GAN. And of course, this required a lot of manual effort to try to find what combinations of principal components and layers would result in a semantically useful thing, right? And here at the bottom are some GIFs that are just kind of showing, like, this one here is like the aging GIF. This one here is like the white hair, GIF. This one here, I think, is like the angry GIF, right? And so we have this running downstairs. Again, thanks to the effort of Zhengyi and my lab students, this took a lot of effort to figure out. So here, this is like the GAN space repo. So here, we have it trained on dogs, Irish setters in particular, right? So here, these are basically GAN-generated Irish setters. Now, I have to say this is not really the best one. So we can kind of keep on generating examples of this by saying resample latent until we're happy with what we have, right? So let's get a better looking dog. All right, this is a pretty good dog. OK, so good dog. So now let's see what happens if we move these sliders around. And I don't actually know what's going to happen, but we can kind of change this as I move it from here to here. Whoop, oh, OK. Kind of what I'm clearly doing is I'm moving the camera around from from left to right, right? So this first principal component is clearly like the equivalent of moving the camera from left to right. And let's see what these do, right? So this one, I guess we're, whoa, OK. You can't move too far, otherwise. This one kind of looks like, whoa.
It gets very disturbing.
I feel like this is kind of like moving the camera from below the dog to above the dog, right? Like it's kind of like looking at the dog from above versus looking at the dog from below. This one's picking up. I'm sorry that this is like a little bit hard to control over the network. This one I can't really explain. This one looks like it's another rotational one. This one's like a zoom in, zoom out one, right? So now I'm going from a dog on the grass to zooming in on the dog's face, right? Whoa, is it gonna work? Whoa, don't go too far off the manifold. So again, I'm sorry, it's kind of like not so. Here's another zoom in one, right? Zoom out, zoom in. Wah. Right? So it's kind of funny that just by playing around with PCA, you can get kind of like interpretations that a human would understand, right? And so the next phase, obviously, is to not necessarily have to have a human play around with these dimensions, and also not to have a human label like what the dimensions mean, right? So once we start talking about language embeddings, we'll come back to this and talk about, okay, so if I have some model for how language works, then I could actually automatically investigate the space and assign names to what's happening, right? So we'll come back to that when we talk about something called CLIP, which is going to be probably a few weeks from now. So it's pretty cool, but that was one of the things I thought was particularly cool about being able to manipulate the GANs, right? Another thing that was cool for GANs around this time was called GAN dissection. This was in 2019, and it was a collaboration, I think, with Bao, was the first author, and it was a collaboration between MIT and IBM, right? So GAN dissection, the idea was to match specific neurons to the presence or absence of image features. So they had an algorithm, or they had a network that could do segmentation, right? So they could say, okay, I've got a good algorithm for taking pictures and segmenting out the trees, right? And from that, I've learned what regions of trees look like. And then if I have a GAN, I can say, okay, well, if I find a neuron such that if I set that neuron equal to 0, the trees disappear in my segmentation algorithm, and if I set that value equal to 5, then I have lots of trees, then I know that that neuron kind of means tree, right? And so they were trying to drill down into very specific places in the network to see what those correlations look like. And so that resulted in a kind of interactive app that was called GAN Paint. So here, this is just like coming out of that GAN dissection paper, where what you're seeing is they select a thing, they say either remove or add, and they can like interactively scribble on the image to turn neurons on and off to produce like, okay, I want some trees here, I want to remove this dome. It was pretty crazy. And I wanted to show you this thing live, but unfortunately it seems like the GAN Paint site went offline between the summer when I wrote my notes and now, right? So if you go to the GAN Paint link, it says demo not currently available, which is too bad. But here you can see some more examples, right? So I can take an input picture, I can rub my finger over the chairs and say, remove the chairs, right? And so this is all basically on top of, I want to say it's on top of StyleGAN, but I'm not 100% sure. Oh man, it's a 47 megabyte thing, so I guess I can wait for this to load while I'm talking about it. But I think we can see here, does it say what GAN it is? Well, you can kind of see, at least see some results, right? So you can kind of scribble to add doors, remove doors, and so on. This was in SIGGRAPH 2019. So it's too bad that they took the demo offline. I'm not sure why they did that. But anyway, so GAN Paint was pretty cool, and people saw that you could actually not just change the whole image, you know, like make the man look older, but you could actually like very precisely put trees here or there. That was pretty cool, right? You could kind of like scribble and say, okay, I like this picture, but I want to put some trees in here, right? That was pretty neat. And so the last thing I want to say is that, you know, all the stuff I talked about so far was basically taking images that were generated by the GAN and playing with them, right? But that kind of means that I can only change images that the GAN generated for me, right? So it's like I'm sampling a Z from latent space. I'm using that to generate an image, and now I can use my knobs to tune that image, right? The exciting thing is, okay, well, what if I want to take a picture of myself and apply these kinds of GAN learned things? I should be able to do that, right? And so the final area of research is basically, embedding real images into the GAN space for later editing. So for example, what I could want to do is I'd say, okay, I want to have some way of saying I want to find over all the possible, if I'm thinking about StyleGAN, W values, some sort of a perceptual distance between the GAN generated by this value and my actual image. right? So this is like the best that the GAN can do, and this is the picture that I put in. And this is basically, some sort of a perceptual loss. And there are a bunch of papers along that line, right? So one paper that I think I listed on the course page was by, I lost my course page. Yes, this one, Abdal et al. ICCV. This is a paper about how to embed images into the style GAN latent space, right? So that's exactly what you want to do. And actually, if you ever used a goofy phone app like Face App, right? There was something around this time, like 2019, where you could download the app on your phone, put your image in, like you take a selfie and then say, make myself look older, or make myself look like an opposite gender, right? That's like exactly how this kind of thing works. You take the, image that came out of your camera, you embed it into the GAN, which is probably like some pre-trained style GAN. Then you can manipulate the GAN using something like what was learned from GAN space to make the image look older, right? You kind of learn what vectors correspond to making the person look older. Now, of course, I just should say, I don't know exactly how those kind of face apps were actually, I don't know exactly what underlying technology. I'm not saying it was GAN space or something like that, but that was the idea. And so then you could do all this crazy stuff on your own face, right? You could kind of morph between you and your friend. You could change your expression by turning a knob, right? All that stuff is basically enabled by GANs, right? So that was suddenly the Wild West of now you could take a real picture and you can edit it slightly to make this person who used to look frowny look smiley, right? So we're kind of getting definitely into some kind of uncomfortable ethical territory where, if the GANs can make totally photorealistic images and they can also operate on real images, well now, you'd have to be pretty good to be able to determine whether a given image is real or fake, right? And that's a whole other realm of research, is kind of image forensics, of making sure how can you trust that an image is real. I know that there was just a couple papers that came out about watermarking images. We'll talk about this a little bit more as we get closer to stable diffusion and so on, because that's certainly become a much more hot topic once you were able to generate images that were out of a particular class, right? Then it's totally the Wild West. Stable diffusion just knocked open the door of can you trust anything that you see? At least in the StyleGAN world, we were stuck with the classes that StyleGAN was trained on, right? So it was dangerous. You might get artificial dogs and cats and so on, but you couldn't get an artificial panda wearing a hat, right? Now you could do that with Stable Diffusion, and it looks pretty good, right? So it's a crazy time to be alive. Okay, so let me pause and ask. Any other questions or comments? We are, in case you're going to preemptively ask me the question, let me just kind of say, next time what we're going to talk about is what are called image-to-image GANs, right? So you may have heard of CycleGAN, Pix-to-Pix, GoGAN. We're going to talk about that next time, okay? So the difference between today's stuff and that stuff is that, today's stuff is still going from a latent vector to an image, right? These papers are more like going from an input image to another image, right? So that's kind of what I mean by image-to-image GANs. And the second half of next time's lecture is going to be talking about how artists, fine artists and digital artists who don't know anything about, machine learning necessarily, appropriated GANs and started making cool art with them, right? And so we'll talk a little about several prominent GAN-based artists next time too, to bring it back to the creativity side. Okay, so questions or comments about anything? I think I went through all make sure I didn't miss anything on my slides here. Oh, this is what I want to show you. This is like the GAN, the top row are real images and the bottom row are embedding those images into the appropriate GAN, right? So this is like saying that I can generate this image of Obama by embedding it into a style GAN 2 trained on faces, right? And this is the best Obama that it can make, right? And so sometimes the images are a little bit fuzzier, a little bit blurrier, but they still look pretty convincing. And then once I've embedded the faces or whatever into the GAN space, then I can do stuff like morph between them, right? So this is like taking De Niro and Hugh Jackman and doing a morph between them. There are lots of ways to do morphs, but this one is in particular leveraging the underlying GAN space, right? Or Oprah and Scarlett Johansson. This one I think is a little less convincing, but this one is pretty good. Anyway, so that comes from embedding real pictures into the GAN space. Okay. Anything else we want to talk about here? All right, so with that, I think that's all I want to say about these GANs. Again, like I said, there's like many, many options. If I didn't talk about your favorite GAN, rest assured that you can tell me about it if you're a graduate student on the next homework, right? So let me stop recording.